So yeah, at this point, I think we're ready to go.
Okay, awesome. Well, can I kind of introduce you, Derek?
Go for it.
And the project. So thanks everybody for coming. So Derek has been working super hard on a variety of just really awesome like technical coding, firmware, hacking, building, debugging, and then demo creation to get all this stuff working. So I'm personally really excited to see all the work you've been doing here, Derek. So PicoG, what is PicoG? It has a cool logo and URL, and what PicoG is a tool for running LabVIEW on microcontrollers and more. And Derek's going to tell us what exactly that means. You can go to the website, picog.org. Derek and I and Nathan Beesmans had some meetings a while back on LinkedIn chatting, and we discovered that it's possible to do this. And it's taken a bit of work and getting under the hood. And we're just really looking forward to showing you guys this stuff. And so take it away, Derek.
All right. So yeah, so PicoG, why? So there's a bunch of people saying that the website is down. Maybe my cache is keeping it alive. We'll have to look
into that. The website's down.
Yeah, so maybe you want to check that while I'm talking here for a second.
That's awesome. We're getting that much traffic. Sweet. So it works for me, and that website is also hosted on GitHub. It's a GitHub page, so I can't imagine that it's being DDS'd, and it's all
people are
static code. So
now putting the full link in chat. So
you could share your screen and show them what the website looks like.
Yeah, I sure can. So it's basic information about the project, how to get started, where you'll find the resources. Basically, it'll link you to repositories and getting started information.
Disclaimer,
code.
Disclaimer, it was my responsibility to get all this stuff up there for kind of download. Please wait till the end of the presentation before you start installing stuff, because we do need to get you kind of the latest and the greatest. We've been working to kind of get it all together. So thanks for your patience there.
So why? LabVIEW is a pretty approachable programming environment. However, hardware tends to be expensive, and us makers and hackers love to interact with the real world with the projects we make. And in the rest of the maker community, there are these amazing boards like the RaspberryPi Pico that were released not long ago. It's $4. If you're making your own custom chips, you're getting to that level. The chips are $1 a piece. And then Raspberry Pi has just released, although it's pretty much sold out everywhere, a $15 Pi Zero 2W. So it's a little teeny tiny board. Actually, I probably should have had something comparable out. That is this size. This is one of the older ones, so super small. But they finally updated their Pi Zero to match the hardware specs of the newer Pis, but in the zero footprint, so built-in Wi-Fi, and just stuff that would be great to be able to leverage from the LabVIEW environment. And there's stuff like the Links toolkit. There's the old Teledyne. Was it Teledyne or TSX Experts? LabVIEW Arduino compiler for the Arduino chips. But there's all these great boards out there that'd be great to leverage from LabVIEW. And Links toolkit works with microcontrollers, but it doesn't work on microcontrollers. That's what this is.
Hey, Derek?
Yes.
Probably a lot of people know this already. Many people might not. The difference between those little boards, there's like the second one you mentioned, the Pi Zero 2 versus the Pico. One's a microcontroller and one is not. What's the fundamental kind of difference between these boards?
Yeah, so the Pico, I'll unplug this one here. So this little Pico and like a Pi Zero, very similar form factors. But this one typically has more I/O with it. So it'll have stuff that lets you talk to, well, just use digital inputs, outputs, buttons, LEDs, kind of like the little Knight Rider lights that were going earlier. It's also got digital communication buses for I2C, SPI, UARTs for talking to things like GPSs, accelerometers, all sorts of fun stuff, analog to digital converters. And then the single board computer.
The first one, the Pico, has all that stuff with the microcontrollers. Yeah.
And then a full single board computer will typically have more stuff like expanded storage, video output. A lot of them, pretty much all of them these days will have USB. So they're pretty much computers where you can hook up keyboard, mice, get a display hooked up to them. And a lot of them these days do have I/O capabilities, but generally not as much as some of the microcontrollers that are available. A lot of them will have a lot of the same capabilities, but they're meant for running larger applications, doing things like multitasking. So just like NI and LabVIEW, there's LabVIEW and then there's LabVIEW real-time. Microcontrollers are typically used for more performant or smaller form embedded things. And it all kind of gets blurry when you have single board computers in this form factor.
Nathan gave another good add-on to that too, which is that the RPi Pico, that cheaper one, it has no operating system at all. Whereas the Pi Zero has a whole operating system. You can choose which operating system, right? Like it has Linux, for example, right? And so for the Pico, if you want, really that's meant for I/O. So in the LabVIEW world, like I think maybe people could think of like the Pico's more like LabVIEW FPGA, like an R series FPGA, in that you run your code and it kind of runs more directly on it without an OS. And the Pi Zero is probably a lot more like a compact real RTOS, like the operating system part, LabVIEW RT.
Yep. So we've got all of this available out in the world, and generally you have to become experts in those devices in addition to your LabVIEW knowledge to be able to use them in LabVIEW. So we're here to say, as soon as I focus on the right window, that you can. So our PicoG tool that we are working on, our suite of software, lets you deploy G code to these targets. Now we are accomplishing this from the GWeb development editor. So that was formerly the NXG WebVI offering that is now its own separate project. Which is great because it opens in about 20 seconds instead of 20 minutes and has a much smaller install footprint. So what does this look like? What does this workflow look like these days? So I'm going to go swap over to my virtual machine. Here is our main desktop application running. When you first start up, you have no devices or applications configured with it. Eventually, we'll have like a whole getting started walkthrough, make it as easy as possible in the application for people to get started. Right now, this does nothing. But fortunately, I know the steps. So I'm going to add a device. This is all plugin based. So this will get to expand via plugins to more targets in the future. But right now, we just are working on the RP2040, which is the little processor chip that is on the Pi Pico and a handful of other boards. And apologies, my VM is doing serial super slow. I've probably had too many customer support cases with Visa and some other stuff that have gummed up the works. Normally it runs faster than this. All the UI stuff is nice and flashy. All the Visa stuff is a little slow. So I know that, so COM1 is just one of the system COM ports, and COM3 is what I've got this guy attached to. So this is just running on a USB connection to this hub, which is hooked into the computer. So it's just USB, shows up as a virtual serial port. Yeah, Michael, right now the Pi Pico is the only target that's supported at the moment. So that UI is going away. It's querying the firmware that's running on this. So I've already deployed our firmware to it, and it identifies it. We've got some tags that identify the actual board type, because SparkFun and Adafruit have their own variants of it. We can see the serial number, the firmware version, and yeah, we like this. Yeah, we can look at its information there. I've already had this set up, so I've already got a name attached to this, but you can rename devices and it'll actually persist on the device for any of the devices that have that capability. So the other thing I want to do is add an app that we can deploy.
Oh, and hey, Derek,
yes.
Folks are mentioning that they don't see your screen right now.
Oh, I'm so sorry.
They only see the hardware.
So let me do that again. I can remove that app. So we'll do that again.
So you're adding a device here?
I'm going to add a device, pick the RP2040 platform. This is what I'm saying. Eventually, we'll have additional targets that are supported. And then there'll be even more tricks we pull in the future as we get more time and or help. So stick around to see what more ideas we have. But so going to let it enumerate the COM ports that are available on this machine.
And this is Max right now, right? This is Visa looking for stuff.
Yeah, it's just everything Visa is really slow, and I'm not sure what or why on this virtual machine. For anybody that follows my my Twitter account or LinkedIn has seen me posting about some of the woes I had to nuke another virtual machine over the weekend as I was trying to wrap up some demos and new features for this. So I'm stuck with this really slow one. But yeah, so this is where it's confirming the information that it queried from the device. We do have different pictures that are available for different boards, and I'll be demonstrating that here in a couple of minutes. But we've got this device, shows up here, can rename it if we want to. We'll follow the device along. So now I'm going to add an application to watch. I had the sweep one running on it, so I'm going to do the standard hello world of microcontrollers, which is if it's got an onboard LED, blink it. If it doesn't, add an LED and blink that. So because I've got my device configured on this second page, I can select that device from this list and hit deploy. And eventually we're going to have features like built-in terminal and just watching the communication that happens back and forth, kind of like how the Arduino environment has a serial monitor built in. We will have those kind of capabilities built in as well. But we can already see that now the onboard LED is blinking. Very, very blurrily.
There we go, yeah.
Too many wires in the way. There we go. And just to prove that this isn't just smoke and mirrors, who wants to give me a number from, let's say, 50 to 300?
42, Michael says.
155. So this is, let me switch back to my screen again. So again, this is in the GWeb development is where we initially run this. I'm going to come back here to view this app list. So this is currently blinking at approximately once a second full duty cycle. So I'll just swap this number to 155. We'll save that. We'll do a new build. And we'll see that it blinked this application here. It's timestamp updated. So I am now going to deploy this again. And we should see that LED blink rate update. So now it's blinking faster.
And it's a little hard. It's a little hard to see how fast it's blinking just because of the frame rate, I think.
Oh yeah, probably across the video feed. Yeah.
Sampling considerations there.
Yeah, Matt, Hopin's a little slow, I've been finding. You're probably getting 2 frames per second. Okay, so you're just seeing an either always on or always off light. Awesome. Yeah. Okay, but yeah, so this is so actually I think that's the initial demo. Those are the application features developed in, you write your code in the GWeb development platform, and we'll look at some more complicated demos in a couple of minutes. Oh, is my webcam running faster? Yes.
I think it is, yeah.
So I'll switch this back to 500. Save. Build.
Oh, there are folks mentioning that the Night Rider code was showing up fine before Jim showed up.
Oh, okay.
So I'm going to turn off my video, and then maybe that'll help.
So now it's blinking slower. Well, hopefully the recording will be high enough fidelity to.
Okay, good. We've got one person out there that says they believe us.
Yeah. All right. Fantastic. Yeah, so we'll take a look at some more examples. We'll get to all of the questions about limitations and current limitations, because there certainly are many at the moment. So picking back up with the presentation. So Ryan Porter asks, why did you choose GWeb development instead of LabVIEW? We will get to that in this slide. So this is based on NI's open source engine that runs via assembly, or VI assembly, otherwise known as VIA. So it's the Vireo engine. It is open source. You can get to it at GitHub. I think it's MIT licensed. It's one of the open source licenses. And it is what NI created to basically power web VIs running in the browser. So nowadays it's not web VIs, GWeb development. But yeah, so we based it off of this. This is a C++ based engine, which is intended to be built and translated to JavaScript or WebAssembler to run in a browser. But it is also intended to build for command line usage from desktop systems. Although running it on a desktop system from a command line doesn't provide much usage. Desktop systems don't have I/O that you can really use. And those features didn't exist in Vireo to begin with. So we filled in a lot of those gaps, added I/O capabilities and some other abstractions and build system modifications to support, to enable this kind of project. First, it powered Lego Mindstorm. Yeah, I believe that is right. So LabVIEW does not give us that via output. GWeb module gives us this nice translated text file that we can then do stuff with. There are some projects out there in the wild of people that are using like VI scripting to programmatically traverse a block diagram and translate that into C code. And eventually we'll be doing things kind of similar to that. But the nice thing about this VIA is it does use a very similar execution engine to regular LabVIEW, in that parallel code paths do run in time-sliced parallel. So there's kind of multi-threading available in it. The execution engine is actually single-threaded at the moment, but we'll talk about that a little bit more in the future.
Yeah. And so just to add to that, at a high level, why did we choose GWeb? Well, because there was already a runtime engine written in C++ that could be compiled to run on microcontrollers, and that runtime engine executes the output of GWeb, and so it was very natural. And the other nice thing too is because this is being actively developed by NI for GWeb, it's presumable that we'll get more features and functionality out of it in the future. and we've got a real, it's got a nice user interface to it. So it was really, low-hanging fruit for being able to run G code on microcontrollers.
Yeah, we could start with an already existing platform, prototype, proof of concept, and we'll be moving on from there. So what we did is we turned that Vireo into our PicoG firmware. So we have migrated to a new build system. Vireo was just a regular make file based system. I've got my opinions about CMake. However, when you're doing things like supporting a Pi Pico, that its SDK leverages CMake, your choices do extra work to wrap that in Make or just use CMake. So we're using CMake, but we have built in a pretty nice abstraction and configuration system for having different capabilities and functionality available for different targets. So as we expand this out, we'll be able to customize the firmware for specific boards. We've added additional shell features, so I'll show this off in the next demo. But again, this was initially already had capabilities of running as an interactive shell, although all you could do was enter in an entire source in a single line, which included the entire source and the instruction to start it running. So we added it to be able to persist via that was sent down, which is great for embedded devices that don't have a file system, things like that. Added some more reporting and board identification capabilities.
Initially, we were thinking of doing something similar to MicroPython.
MicroPython.
Yeah, where basically it's got like a folder. It shows up as a thumb drive, and you can drop your files in there. However, the route that Derek kind of really recommended and has been working on is allowing the board to plug in to the PicoG Desktop software, and there's kind of a set of high-level commands for doing things like sending new firmware, resetting the board. So it has a serial protocol.
Yep. And then adding I/O capabilities, which is what you want when you're running on embedded boards like this.
Yeah, and also too, just to mention, people ask, why the Pico? We went the microcontroller route because that board has been really popular, and it's a $4 board. Plus, it does have a lot of limitations because it's small, and so it's kind of a nice case for what can we run on something super tiny. And Derek will talk about some of the limitations, in particular like memory and things like that. But to use that as kind of the starting point and then add more kind of on top of that. And these boards are just going to have more and more memory in the future, right? Get cheaper and cheaper. Yeah.
Yeah. As far as small targets go, the Pi Pico is a giant, which made it easy. So along with the firmware, we've got GWeb APIs. So we have got a bunch of stub VIs that install into palettes. You'll notice there, it's only kind of drawing a corner of our logo. There's a couple of bugs in the GWeb development software at the moment. And as I discover them, I'm submitting them. But yeah, so you get these palettes of these stub methods that you can develop your block diagram logic with. So we've got functionality for things like GPIO, some standard I/O stuff such as printing formatted text output or reading input, so we can actually read text input from a command from a terminal and work with that. And these are stubs that just have known names that our tool, our PicoG Desktop application goes, hey, I know that name. I'm going to replace it with the actual low-level call that needs to be made. And then that processed and translated via is what gets sent down to the target. Oh, looks like I forgot some stuff here. But yeah, so PicoG Desktop tool, we saw it. It's got plugin-based target platform support, so it is extensible as we add support for more devices. It does web app management and device management. We saw it's kind of got like little mini Macs capabilities to it. And it also stores preferences per user. And then as we build it out, I'm sure there'll be some that are system-wide, but we're still expanding on those capabilities. And again, for anybody that's seen my fun I was having the end of last week and over the weekend, the plugin-based target platform support, LabVIEW tends to not really like, but we're pushing through. Moore's law will be dead the same year we get cold fusion. There's always workarounds. Yeah, so future plans. Excuse me a second. So obviously, we'd like to expand to more targets. Right now, it's just the Pi Pico. It's just the Pi Pico. We do want to expand to an ESP32, which I've already got on a breadboard here. I just have to get up to speed on its tool chain. And then, Raspberry Pis, the actual single board computers, not just the microcontrollers, and anything else with a reasonable memory footprint. And we have GPIO and some STD standard I/O capabilities, but we need to expand to more, such as the analog capabilities, communication buses, things like that. One of the things we are going to need to push for to make this more than just a pet project and actually usable is drastically optimizing how Vireo uses memory. We are with a handful of VIs. You will quickly hit the memory usage ceiling on a Pi Pico. It currently dynamically registers everything in RAM, which isn't something that's always necessary on microcontrollers. Microcontrollers can run code directly from the firmware and storage. It doesn't have to load it to the separate random access memory that they have. They have two sets of memory, the persistent storage and the RAM. And right now, Vireo loads everything into RAM, which then takes away from the space you have available for loading your dynamic programs. So we, once we get some of this baseline, more of this baseline functionality and workflow nailed down, that'll be our next big push. Tuan wants machine learning built-in functions. I'll point you at an NVIDIA board. We are also interested in multi-threading. The Pi Pico has 2 threads, has 2 cores. It'd be cool if we could leverage both. However, right now, as I said, Vireo runtime is single-threaded. NI is working on getting back to enabling multi-threading as things like WebAssembly add in threading support. They will be interested in leveraging that as well for performance. And we would certainly love to take advantage of that as well. And then, once all of the baseline stuff is done and we're performant and we can actually load meaningful sized applications, then along will come peripheral libraries, just like you're familiar with from the Links toolkit or the Arduino, where you have servo libraries for doing the 2812 adjustable ADs, things like that.
The Pico is also interesting because it has those PIO, programmable IO. Like it's got these, I think there's 2 or 4. Basically, they're kind of these little independently running state machines that kind of run pretty fast at hardware level. And then that, I think, is the basis for some of the standard libraries that do like I2C, SPI stuff, right? And they can even be kind of like reconfigured if you like compile the firmware, right, to do that.
So people have used those to enable things like network ports. However, using that will require something that's in the right side bullet on here. So we'll go through those real quick. I'm
hearing people want some demos too.
Okay. Yep. Definitely. So on that, one of our future plans is to actually generate the firmware from this source. So we'll actually take the VIA, translate it to C, C++ source, and then use the tool chains to build that, which will work around all of the memory limitations, all of, you know, any of the runtime performances that we're taking from this being, it's not interpreted. It is better than interpreted, but it is, you know, not bare metal code. And using things like the PIO require extra build steps in building that into the firmware. So those will be things that we can enable as we get to the performance optimizations beyond just the memory optimization. Cool. Okay, so more demos. So everything I'm going to be showing off is going to be single VI examples. So when we first started up, we had this sweep example. So basically a single main loop, which just uses a shift register and a, you know, either counting up or counting down once it gets to the end and it's no longer in the range. It changes direction. So here is a slightly more interesting example. I'll just go ahead and build and run this, and then we'll take a look at the code. So I'll go ahead and get this built. I will add it. And we'll go ahead and deploy it, and hopefully it succeeds. It started to, and there we go. So back this up a little bit. So now we've got the 10 bar graph there, and I've got these two buttons here. Every click I can move to the left, or I can move to the right. So now we're actually reading in some input, doing some stuff from the real world. We will get to that, Alexander. That is actually the next slide when we get back to the presentation.
There's a form. There's a form on the website where you can enter your credit card. And then in the comments, just add what feature you want.
Yeah. So I'm hearing while we're finishing this presentation, Jim will get the PayPal going for us.
Just paste your credit card info in the comments.
Almost, Norm. It's not that full-fledged yet, but maybe for Project Holiday Cheer 2022. So this is the source code of this application we're just watching. So we chopped a bunch of stuff out of the capabilities that are available in the runtime to get it to fit into a Pico. So there's a lot of numeric formats that aren't available, like floating point isn't available at the moment, which seems kind of silly. And like once we get to those memory optimization steps and optimizing how the firmware registers its built-in types, you know, we will be able to add all of that back in and much more. But this is example. We've got, you know, a string of GPIO functions here for the left button, for the right button. So this follows, you know, typical LabVIEW programming paradigms. You got some initialization thing, and you do some configuration, and we've got our read function in the loop. Kind of looks like DACMX. Down here, we're just kind of initializing and configuring a whole bunch of pins at once. So these are all the pins on the RaspberryPi Pico that are hooked up to those LEDs in order. And if we somewhere, yeah. You know, so these correspond to these GPIO numbers that you would find in any Pi Pico pinout. So not the physical pin number, but the GPIO pin number, since this is the GPIO functionality we're using. So it maps directly to those. Initialize it, set whether it's an output or an input with a Boolean. For inputs, you can set the pull up or the pull down. And all of this follows the documentation you'd find for a Pi Pico and its I/O capabilities. And then we've got a little producer-consumer setup going here. So queues do work. So here we're just, every iteration, we're reading both buttons, seeing if this is the first iteration that they were pressed. If they are, we're we're figuring out what direction we want to modify the number and sending that to our consumer loop. And then our consumer loop, if it actually gets a value, if it doesn't time out, it modifies what's in this shift register by that, make sure it stays in range so you can't go off of an end. And then every iteration down here, so roughly 10 times a second, it is updating all of the outputs, and it's turning on that corresponds to the index we want turned on. So it's going to be both, Michael. A Raspberry Pi Pico has 246 kilobytes of RAM, and even with all the things we've disabled in Vireo, but then we added in some stuff like the GPIO functionality and some of the other text-based I/O. Just from initializing those capabilities, it's using 150 kilobytes. So we've gotten it to where we've got about 70 kilobytes, but every instruction that gets registered takes up at least 300 bytes. So, instruction-wise, it's pretty expensive. If you've got in regular assembly, a single instruction might take 10 bytes, but when it's taking 300 bytes, that's a huge jump in memory requirements. So, once we finish this workflow, in the last week, I did a huge refactoring from an older version of the desktop application to start supporting some of this plugin-based platform support and app listing and the device listing, the device manager capabilities. So once all that gets nailed down, it's back to whacking at the firmware a bit more.
And Derek, did you mention anything about like the minification of the VIA and stuff like that?
Nope, not yet. So let's take a look at what else is.
The VIA is kind of cool. Yeah.
Running behind the scenes, and we can actually see that in the app. So Jim actually hasn't seen this yet. I added this morning.
Yay.
So we've got these applications. So this is the source as spit out directly by the GWeb development software. So this is the VI assembly. So they'll start off at the top by defining a VI as a virtual instrument type. It'll set up the locals for the local data space. If there's any kind of I/O points that would typically hook up to front panel controls in a web browser, you'd see some other definitions there. And then it gets into the code. And if you get familiar with this, you would notice that there are these clumps, and they kind of correspond to discrete chunks of block diagram code. And you'll have different clumps, and each one of them can run in time slice, and that's how the Vireo execution does its like parallel processing. But we take this and we pass it through a couple of functions, part of which is defined by the platform plugin, so that if we have instructions that are only available on an RP2040 versus things we can get access to when we move to the Pi Zero or other Raspberry Pi boards, they would have the ability to do some of their own replacement. But we can actually preview what the output looks like. So this is, I'm going to go ahead and copy this out. So we have 514 lines. It is almost 16 kilobytes long. And we're going to preview what this processing looks like. And we'll notice that now there are some new functions that have shown up to replace some of these other very long names. In addition, it puts all of the definitions for those stub VIs we have. The GWeb module puts them in the output file, but we actually don't want those. We don't care about those. So if I paste this in, we are now down to 8 kilobytes. So we've just about halved it. A lot of that was in there just to have it so we can put some code down in GWeb, but we do other things like...
One thing I was going to mention that we did is like all the variable names like kind of come from the VI, like the control labels and the things like that. And so we were able to go through all the constants and the variables and change their names into just a bunch of like numeric that just kind of increment up. So the code becomes pretty non-readable at that point. And then there's also ways that we can optimize by even removing some like little dead branches, because the VIA compiler actually leaves a lot of kind of dead cruft in there sometimes.
The VIA output has zero optimization done on it. It is a direct translation of the block diagram code. If you've got an error output tunnel that doesn't go anywhere, it shows up in the VIA.
Yeah, and when we send that over to the microcontroller, it actually keeps that in memory as a string and then executes it, right? And then it creates variables by those names for the future when everything's coming by interpreted. One of the things that we were thinking in terms of even further reducing space would be to take all of the like the primitive data type names and function names and even like crunch those down into a more even like maybe a fixed width, different data type, more kind of numeric operation codes.
Well, if we get to the static,
that's a bit of work, right?
Yeah, if we get to static code definition instead of this dynamic code definition, we wouldn't really need to do that.
Yeah, exactly.
And what does this look like from a command line? Also the other thing I got to show off is
so Michael asked, one can add external RAM to the RPi Pico. Would that help? And I think my understanding is then you have libraries that can access it, but it's not really, I don't know if it's necessarily accessible.
Yeah, so that's the flash storage, that's program storage and space you have available to write data to if you're doing like data logging, but that's not actually RAM, which is the limitation here. So this is a 2 megabyte chip. Right now the firmware is just under 500 megabytes. So we've got 1.5 meg of program storage we could use, but we've got such a small amount of RAM to load that into that it really doesn't matter. It's not RAM. It's flash storage. The Pi Pico's onboard 2 megabytes is the flash program storage. But yeah, so I unplugged and plugged this back in, and without doing anything over at the computer, it's running again. So this does actually deploy it to the Pi Pico, and it does run. So after you get it deployed to it, we've worked out, plug power back in, and after its initial boot up, it will run. And as we said, this is basically all terminal based. So if I open up PuTTY here, I can connect to it. I'm going to hit Control-C a couple of times to stop the running application. And we can do things like show the program listing of what's in there. Again, serial is really bad on this VM. But it's not even gonna, it's gonna lose data before it finishes receiving everything, and it's like missing new lines and stuff. So we can reset, we can reload what's on there, we can do stuff. So these commands are exactly what our desktop tool uses to query the device. So we can see what board variant it is, what platform it is, so we know which plugin to handle it with. We can see its serial number or ID, what its configured alias was if I want to rename it.
Can you zoom in the font on that a little bit?
Maybe.
I think so. Change settings. I think the change settings there, maybe. It's not too hard if it's, oh geez.
I'm getting there.
While you do that, I'm curious in the audience, who is interested in helping us like extend the available RAM and do some of that stuff in C++? Are there any firmware microcontroller developers out in the audience? I saw a good comment from Peter Horglid saying Pico supports XIP and can run code directly from Flash. It's kind of cool.
It does, but again, with this VIA implementation, we have to load and run VIA, and each one of those registered instructions takes a certain amount of RAM. We're not creating firmware here. That's why that's on the down the road plan, is to take VIA and translate it to C++.
Yeah,
and then actually build firmware. But this isn't the problem we're running from Flash.
The problem is we have to load that whole VIA in memory, and I don't think we want to, like, when we send VIA down, I mean, I guess potentially it could be kept in Flash, but then it's like doing a lot of stuff behind the
scenes. So we are storing the source in Flash.
Yeah.
But then it's got to load the instructions into memory. And the instructions aren't necessarily the source. And in fact, a lot of times it's bigger than the source because it has a whole bunch of type inspection and instruction information. And there's a bunch of stuff that the runtime is setting up for each instruction and for the clumps. So yeah, unfortunately, like we can expand the Flash, which would let us put larger VIA source files, those text files, onto Flash. But then to run it, it needs to get loaded into memory. And I think right now, with some of the experiments Jim was doing, we get to about 3 or 4, not super tiny, but definitely not big sub-VIs, and it would run out of memory when it was trying to load into the runtime.
So I was just, folks have offered to help. I'll just mention on the PicoG About page, and yeah, you need the www in front, Tuan.
Oh, is that what it is?
Yeah, maybe we need to fix that. But we have an About page, and we certainly would love sponsorship. I think even more, I don't think money is really the limiting factor. I think it's people's like time and interest and enthusiasm on a project like this, at least at this point. And so, if people are really passionate about LabVIEW running everywhere and having open components of the LabVIEW stack, such as this VIA intermediate representation for executable block diagram code, and an open source runtime engine for this intermediate representation, plus all the tooling on top of it, please reach out and get involved. I think in general, where this is moving is really exciting.
Some of the, I did point out.
Derek
a couple
gets really
of other
excited about the low-level stuff, though. I get excited about the working
well,
together.
I've definitely got some very intended projects for this once we get to the point. So there's a toaster oven that I've gutted, but I'm not really going to be doing anything with it until this is done sufficiently enough to where I can write temperature controller code for surface mount surface mount soldering. And I want to implement the oven control in LabVIEW running on a Pi Pico. So yeah, I'm just, let's see here. Back to the screen. So one of the things I didn't show off is this is sorting by updated time as well. So if I go back to the sweep component and build this, so right now sweep's at the bottom. But if I build this, it'll blink and now it's up top. You can resort by name. So yeah, just some somewhat nice features to have. Oh, I've still got PuTTY open. Oh. But yeah, so any questions? Let's see, if you manage to get 5 volunteers working with that part-time, how long do you think it would take to run an aquarium controller out of this platform? What all goes into an aquarium controller? Is that doing like data monitoring for temperature and
probably some pH? Michael, are you willing to donate an aquarium to the cause?
But running pumps, running aerators, I can see all that stuff being done.
We can heat it with Derek's toaster oven.
So we don't have the analog features right now, but we do. Those are like the next to be provided, and then a state machine like that would certainly fit. How much will
Derek?
this? Yep.
One question that I had: did you demonstrate any of the serial communication? Like,
I did not.
That's kind of cool too. We have a few minutes. Is that working or maybe not?
That's actually what I was just about to check.
Oh, awesome. Yeah, we've got like a few minutes. So this is a really cool part of it too.
We'll see if GWeb wants to build it.
You're connected over the serial port, and the PicoG Desktop is sending these high-level commands to basically like run Vireo, basically, right? Like, what kind of board are you? Here's some Vireo, run it, stop running it. But there's more you can do with that serial, the USB port, right?
Mm-hmm. Okay, so yeah, right now, because this is the source and I've got the package installed with the palettes, it's not, I have to uninstall the palette. Because the source stuff that I have those demos implemented in for testing the processor conflict with the installed palettes.
Oh no.
And I can't just copy and paste. But yeah, so this is something that works. Simple state machine. Unfortunately, enumerations don't work for some reason. I haven't dug into that too much. But so it's a numbered state machine. And this is something where you spit out a prompt, say, hey, enter a number from 0 to 1023, because I've got 10 LEDs there. And 2 to the 10th is 1024. So you enter in a number. It's going to prompt you to enter in a number. And then here, it'll keep looping in this state, so it'll stay in this.
And we don't see your screen again.
Oh, I did it again. Sorry about that.
Yeah.
Yeah, so numeric state machine, because enumerations don't work.
Yeah.
But so display the prompt, go to the state to accept the input, and for every character they type, we add it into this. We concatenate it with a string. Once they enter a new line or a line feed, we'll then transition to the last state. And then this is where I basically take that number from string representation, change it into an integer, make sure it's in range. And then we actually can set the binary representation of that out on the LEDs. So right now, Steve, serial, that is one of the reasons why the next target to work on is an ESP32, because the ESP32 has Wi-Fi and Bluetooth. And we are going to have that optimization work to do ahead of being able to get that integrated. But stuff like the ESP32 is planned to be on like Wi-Fi, and you can put in the device's IP address from the desktop software instead of picking a COM port. And you'd be able to deploy code and interact with it over a network, and then we'll expose any of the features that the underlying hardware have. So not there yet at all, but those are all planned. Are all GWeb primitives supported? None of the JavaScript integration stuff is, because we're not running in a browser. So things like WebSockets and integrating other libraries don't work. You basically have to, any of the string processing, the math stuff, all of that is in there. We can actually take a look at all of the instructions that are available in this little guy. So it's got a whole bunch of stuff in here, and it's not even going to be able to finish loading the full list because of my serial problems. But there is a whole bunch of array manipulation stuff. Occurrences are in here, string processing. What else do we have in here? Math stuff, logarithms, trig. So all sorts of stuff are in here. Just about everything that is available in GWeb that doesn't rely on the fact that it'd be running in a web browser. The Cutie Pie. So, oh, that's what I haven't shown that off. So I've got this other device. It is also a Pi Pico, but I've built the firmware on it to say that it's something else. So I'm going to get this plugged in. We will then use the tool. So let's add another device, and then I'll answer questions while Visa enumerates it very slowly. Yeah, so handling a shield would take up a lot of resources. That's, you know, we've got a couple of workflow features to work out. Come on, Com4, you can do it. You're registered in this VM, right? Do I have 2 Picos here? I do not. Well, that won't work. Get the second Pico here, please. I have another virtual machine open. Oh, come on. Yay, live demos.
Okay, well, we're getting close to the end of our time here. So I think in terms of next steps, we're going to be pushing out a release here shortly. I was supposed to get that out this morning, but we'll have something you guys can download and play with by the end of the day.
Well, 0.0.4 is up on GitHub.
Okay, great. The firmware?
The firmware, yep. Ah, here we go.
Yeah.
Com4. We're going to wait another minute for it to finish enumerating.
We're 1:01 p.m. on my clock here, so I'm not sure if they need to bump us out.
Yeah, we're a minute past, but we still got 91 people hanging on.
Do they need the room for something?
who we're stealing views from. Actually, so this time they have it set up so that each presentation is its own room.
Can go as long as we want.
So I've got this configured to show up as a SparkFun Pro Micro. So there are even just with the RP2040 chip, there are different variants of it that'll have different I/O, like the Adafruit, Feather, and Trinkets, and some of the other boards. You know, have other built-in peripherals on them, and our plan is to expose that and leverage that with this platform. So we already have the capability of enumerating different boards in our build environment. We've got that all extracted out into different platforms where you can have you know, different tool chains, and then in those tool chains you can have different boards, which eventually you would have potentially different functionality that gets included in the build. Right now we don't, because we just have GPIO. That's more or less the same everywhere. But the idea is to eventually you know, have board specific capabilities that are added in. Yeah, exactly, Steve. That's why we started from that. And you know, for aside from doing a couple of neat blinky lights, and you know, more than that, but not anything much larger than a state machine. You know, we've got some work to do. We know what we want to do. It's just the time and effort to accomplish that. But yeah, especially the next step, getting to the ESP32 and getting network connectivity and access will be huge. And once we get that, so even the Pi Zero 2W is really attractive because that has gobs of RAM compared to these microcontrollers. And we wouldn't need those optimization steps to get something running on the $15 Pi Zero 2W. And then way further down the road.
Yeah, and so if we get this running on these embedded platforms that have an OS also, and we're kind of plugging in the various libraries and mechanisms for doing TCP/IP, file I/O, and stuff like that, then at some point there's really no reason why this can't do a host of different things, right?
Mm-hmm. Yep, and then way further down the road, when we can actually start generating C++ code translated from the VIA, that'll open it up to anything you can write some base layers for, like AVRs and Arduinos and all of those other stuff. But for now, we're doing this nice runtime because it's got the clump execution that runs LabVIEW code like LabVIEW code. Yeah, it's a starting point. Michael really wants an AT89. We're going to get that AVR Atmega 328 first, because I've got gobs of those. Then probably a 32U4, I would imagine. I don't know that you can do the AT89 platform board support. Yeah, it's I haven't migrated any of my robotics projects off of Atmegas because I've already got all of my libraries and stuff written. But doing this in LabVIEW would be the jump once it would get it capable enough.
Well, I'm really interested too in the topic of looking under the hood at how is VIA structured? Like how do you do kind of a text-based representation of G code? And there's lots of different potential ways to represent a synchronous data flow block diagram. Yeah, it's really fascinating. And so as people start to kind of think about this, then the question is like, well, how does an execution engine run? Why can't we code all this stuff up in LabVIEW?
Yeah, so if you go to the Vireo SDK repository, it does have some documentation on the VIA source. And it's not 100%, but it's pretty good and definitely explains all the core structure and how things are defined. Soon. So yeah, so this is up on GitHub. You can take a look at it. You can curse me out all you want, and then after you curse me out, give me all the suggestions or implement them yourselves. That's what we're here for. We're here for more contributors. So Jim and I have our huge list of issues we're already submitting to ourselves. And you can certainly submit your own and grab some of them and start working on them. So there's PicoG for the desktop app and the GWeb palettes, and then there's PicoG Firmware for the firmware. So there is a bit of work to get a development environment set up and working for the firmware. The wiki actually has, the wiki on the PicoG has those instructions for how to build the firmware. It'll link show all the stuff to get in your environment set up. I need to edit this. There we go. Next. Okay, we're finally down to half crowd. There are other sessions going on. Yeah, hit us up on GitHub. Hit us up on LinkedIn or the Twitters, and let us know what you got.
All right, cool. Seems like everybody's happy.
Huzzah! Wait for the issues to start rolling in.
Oh yeah, nothing works.
Yeah, I think this week's project is definitely going to be setting up another 2020 virtual machine that doesn't have all of these issues.
Totally, huh?
The rest of the app is nice and snappy. Oh, I wasn't sharing my screen anymore anyway. That's all right. There's still 33 people watching. I'm tempted to.
What do you guys want us to talk about, guys? We're still here.
Tempted to hang around till they all leave, or keep asking.
Well, we gotta put them to work. Please do.
I'm surprised everybody didn't immediately jump out for Eric Reffitt's lesson learned from NXG.
Doesn't matter. Just get back to work, guys. No, it's important stuff.
Lucian, the recordings will go up on the LabVIEW wiki once they finish processing all of them and get them transferred over to. I'm assuming they're going to put them on YouTube or something, and then link to them from the LabVIEW wiki. But that's going to take them some time to do it. That doesn't directly happen from this convention app. I can quickly show off the workflow again. It is not, let's see, which one do I want this one? It is running. It is running the GWeb module's output. So you write GWeb code, although not that one, because that's shows off some more stuff that we can do, but it's not the one that I can run right now. This one. You write some LabVIEW code in the GWeb module, and then this output is actually what we're running. So when you build this, it generates a text file that is the VI assembly representation of that block diagram, which are then instructions that can get processed by the Vireo runtime engine, which is an open source execution engine that NI has released, and it's what they build the WebVI runtime from. But it's also just a C++ source, and we build it for Pi Pico to generate a runtime engine firmware that can accept and run this via. So it does load all, it interprets it from the text, but it then does build structures of the runtime instructions and the function calls. So it's halfway between interpreted and like even a bytecode representation once it actually is run. So right now we are building firmware for the Pi Pico. So we've got anything based on the Pi Pico's processor. So I've got this guy. Get rid of that one. Like if we take the sweep and deploy it, it starts running it. So the runtime engine right now is built for the Pi Pico. We've got the build infrastructure set up in the configuration for if you did want to integrate different tool chains or different variants of the Pi Pico, you could. So like this is where we have the GPIO functionality defined and translating from the Vireo execution engine and how it structures parameters and things like that into the Pi Pico functionality. But we've got we've got a bunch of optimization to do in order to get it to not require as much memory and be able to do more than demo code that's more than a couple of VIs big. Yeah, that's our goal, Lucien, is just expose more of the Maker environment to LabVIEW. There's Links Toolkit that lets you use LabVIEW with microcontrollers pretty easily, but it's running pre-made firmware, and you get this like transactional. Turn this on, turn this off. You get to do like one thing at a time. You're not actually building and deploying applications. That's what we're working towards here. We'll get there. So we've got most of the workflow and the basic functionality in place. And then we've got some optimization work to do. And then we start to really build out the features and the libraries that are available. Because yeah, getting the right microcontroller, stuff that works on microcontrollers that looks like this, pretty damn interesting. Yeah, these are all kind of so many wire bends. Here, this one's nice and simple. And yeah, and our next target we're planning to work towards is the ESP32. Although probably before we even get to that, probably work on like the Pi 0W2, the 02W, once those are in stock in sufficient numbers. Because then we won't have memory limitations, and we can work on the features before we work on optimization. So which direction is better first? Spread the word. If you know anybody that's good at LabVIEW or good at C++, good at microcontroller code, firmware development, that would be great. Find your other buddies that are interested in LabVIEW everywhere.
Absolutely.
Guess I should show off the code. Other people that have walked away from their computers are still just sitting in this room. All right, well, there's no longer any chats. Oh, I keep forgetting about this QA feature. Did I miss any? Okay, we talked about that. All right, I'm going to head out, Jim.
All righty.
Pleasure presenting with you.
Great presentation.
Thanks for the inspiration and getting this kicked off.
You bet. It's fun for me. Fun to see everything you've done. All right, talk to you later.
All right. Bye, everyone.
Bye.